Hi friends, today I am giving a lecture on example problem on sublattices in discrete mathematics. In the previous video, we are already discussed about what is the definition of sublattice and check whether the following subsets are sublattices of lattice or not. That can be explained with one example problem. In this video, we have to discuss another example problem on sublattices. Please refer the previous video, whatever I am telling, for better understanding of what is the definition of sublattice and what is the example that we are discussed in this previous video. Now we can go for another example problem. So after telling the definition once again, okay. So let us consider L comma join operation comma meet operation is a lattice. Okay. Let us consider L is a finite set. On that finite set, we have to perform two operations. One is join operation, second one is meet operation. By considering the elements of set L, we can take any pair of elements. For that pair of elements, both the least upper bound exists and greatest lower bound exist. Hence, we can say that L comma join comma meet is a lattice. Okay. Now consider another finite set, that is S. S is a subset of L. Okay. Now S is said to be sublattice of L if and only if S is closed under both the operations join and meet. So whenever S satisfies the join and meet operations for every pair of elements, then S comma join comma meet is said to be a sublattice of L. Okay. So once again I am telling the definition completely. Okay. Let L is a finite set. On that finite set, we are performing both the operations, that is join and meet. Okay. When we can say that L comma join comma meet is said to be lattice. Okay. We can take any pair of elements from the given set L. There exists a least upper bound and greatest lower bound. Hence, we can say that L comma join comma meet is a lattice. Okay. Next one. And let us consider S is another finite set. S is a subset of L. Okay. Now S is said to be a sublattice of L comma join comma meet if and only if S is closed under both the operations join and meet. That means for every pair of elements in the set L, it satisfies both LUB and GLB. Hence, we can say that S comma join comma meet is said to be a sublattice of L comma join comma meet. Okay, so this is the definition of sublattice. Now, whatever I am telling here, I am writing this the definition of sublattice. Let L comma join comma meet be a lattice here. Okay, and let us consider S is a finite set. S subset equal to L. That means S is a subset of L. The algebraic system S comma join comma meet is a sublattice of L comma join comma meet if and only if S is closed under the operations join and meet. Okay, so this is the complete definition of sublattice. Okay, next one. Another important point is every sublattice is also itself a lattice. Okay, here from the definition we can say that S comma join comma meet is a sublattice of L comma join comma meet. But this sublattice is also a lattice. Every sublattice is itself a lattice, because whatever the condition is there, the same condition is also applied. What is the condition here? We can take any pair of elements of L. For that pair of elements, both the least upper bound and greatest lower bound exist. Whatever the condition here applied, so the same condition is also applied for sublattice. We can take any pair of elements of S. For that pair of elements, both the least upper bound and greatest lower bound exist. Okay, hence we can say that every sublattice is itself a lattice. So this is only important point. Now consider this example. Consider the lattice S comma division operation. Okay, so S is a finite set. Division operation, division relation can be applied on the elements of set S, represented by Hussey diagram shown below. So this is the Hussey diagram where S is equal to set of 1, 2, 3, 4, 6, 8, 12 and 24. Okay, here S comma division operation or a division relation, so is a lattice. Okay, where S is a finite set, S contains the elements set of 1, 2, 3, 4, 6, 8, 12 and 24. On that pair of elements of S, we are performing the division relation or a division operation. Check whether the following sets M1 is equal to set of 1, 2, 3, 6 and 12, M2 is equal to set of 1, 2, 6, 12, 24, M3 is equal to set of 1, 2, 4, 8, 24 or sublattices of S or not. Okay, so this is the finite set S and this is the relation, division relation. So we are taking the elements of S and the division relation. We have to draw the Hussey diagram. Okay, so this is the Hussey diagram for S comma division relation. Okay, so here first of all, division relation means we can take any pair of elements of S. Okay, if the division relation exists between that pair of elements, we have to draw the edge between that two elements. Otherwise, we cannot draw the edge between that pair of elements. First, I am taking element 1. Okay. Next element is 2. Okay. 1 divides 2. So that we have to draw the edge between 1 and 2. Next element is 3. Here I am writing 3. 1 divides 3. So that we have to draw the edge between 1 and 3. 2 does not divide 3. So that we do not draw the edge between 2 and 3. Next element is 4. Okay. So 2 divides 4. So that we have to draw the edge between 2 and 4. Okay. 3 does not divide 4. So that we do not draw the edge between 3 and 4. Okay. 1 divides 4. Okay. According to the transitive property, 1 divides 2, 2 divides 4. Hence, we can say that 1 also divides 4. So that we do not draw the direct edge between 1 and 4. So, okay. There is according to the transitive property, 1 also divides 4. Okay. Next element is 6. Okay. So 4 does not divide 6. So that we do not draw the edge between 4 and 6. 2 divides 6. So that we have to draw the edge between 2 and 6. Okay. 3 divides 6. We have to draw the edge between 3 and 6. Okay. Now, 1 also divides 6. Okay. 1 divides 3, 3 divides 6. According to the transitive property, so 1 also divides 6, so that we do not draw the edge between 1 and 6. Okay. Next one. Next element is 8. Okay. So, 4 divides 8. So that we have to draw the edge between 4 and 8. 6 does not divide 8. So that we do not draw the edge between 6 and 8. Okay. 2 divides 4. 4 divides 8. According to the transitive property, 2 also divides 8. Okay. So that we do not draw the directly edge between 2 and 8. According to the transitive property, 2 also divides 8. Next element is 12. Okay. Here 8 does not divides 12. So that we do not draw the edge between 8 and 12. 6 divides 12. So that we have to draw the edge between 6 and 12. 4 divides 12. So that we have to draw the edge between 4 and 12. 2 divides 12. Okay. According to the transitive property, 2 divides 6, 6 divides 12. Hence, we can say that 2 also divides 12. 2 divides 4, 4 divides 12. So that we can say that 2 also divides 12. Okay. Next element is 24. Okay. 12 divides 24. So that we have to draw the edge between 12 and 24. Next, 8 divides 24. So that we have to draw the edge between 8 and 24. 4 divides 12. 12 divides 24. So that 4 also divides 24. According to the transitive property, there is a relation between 4 and 24. We do not draw the direct edge between 4 and 24. In the same way, 4 divides 8. 8 divides 24. Okay. 4 also divides 24 according to the transitive property. So that we do not draw the direct edge between 4 and 24. Okay. So this is the Hussey diagram for the relation or division relation between the pair of elements of S. Okay. So now this is called as S24 comma division relation. So this is the Hussey diagram of S24 comma division relation. So what are the divisors of 24? So the division relation is satisfied on the pair of elements of S. This is the corresponding Hussey diagram. Now we are taking 3 subsets of S, that are M1, M2, M3. Okay. Now we have to check M1 is a sublattice of S, M2 is a sublattice of S, M3 is a sublattice of S. We have to verify that. Okay. First, I am taking the M1 subset. M1 is equal to set of 1, 2, 3, 6 and 12. Okay. So here this is 1, this is 2, this is a 3, this is a 6, and this is a 12. So 1, 2, 3, 6, 12. So whatever the elements in M1, that elements are taken from the main Hussey diagram. So that elements can be drawn as one Hussey diagram. Okay, 1, 1, 2, 2, 3, 3, 6, 6, 12, 12. Okay, now we have to check. We can take any pair of elements of M1, both the least upper bound and the greatest lower bound exist or not. We have to verify them. Okay, we can take the pair of elements 1 and 2. Okay, so 1 divides 2. Yes, there is a relation between 1 and 2. Okay, next 1 divides 3, so that there is a relation between 1 and 3. Next 3 divides 6 and 2 divides 6. Yes, so that we have to draw the edge between them. Next 6 divides 12. Yes, we have to draw the edge between them. This is the Hussey diagram for M1. Okay, now we have to verify them. We can take any pair of elements of M1, both the least upper bound and the greatest lower bound exist or not. Okay, we can take the pair 1 and 2 elements. Least upper bound is 2, greatest lower bound is 1. We can take the pair of elements 1 and 3. Least upper bound is 3, greatest lower bound is 1. We can take the pair of elements 2 and 3. Least upper bound is 6, greatest lower bound is 1. We can take the pair of elements 2 and 6. Least upper bound is 6, greatest lower bound is 2. We can take the pair of elements 3 and 6. Least upper bound is 6, greatest lower bound is 3. We can take the pair of elements 6 and 12. Least upper bound is 12, greatest lower bound is 6. Okay. We can take the pair of elements 3 and 12. So least upper bound is 12, greatest lower bound is 3. We can take the pair of elements 2 and 12. Okay, least upper bound is 12, greatest lower bound is 2. We can take the pair of elements 1 and 6. Least upper bound is 6, greatest lower bound is 1. We can take the pair of elements 1 and 12. Least upper bound is 12, greatest lower bound is 1. Okay, so we can consider any pair of elements of M1, both the least upper bound and the greatest lower bound exist. Okay, so for that pair of elements in the main Hussey diagram, so whatever the pair of elements we are taking 1, 2, 3, 6 and 12. So here what is the least upper bound? We can take any pair of elements of M1. So the same LUB and GLB is also exist. We can take any pair of elements of M1. Okay, here in this diagram also 1, 2, 3, 6, 12. Okay, we can take the pair of elements 2 and 3. Least upper bound is 6, greatest lower bound is 1. In this diagram also, for that pair of elements 2 and 3, least upper bound is 6, greatest lower bound is 1. We can take the pair of elements 6 and 12. So least upper bound is 12, greatest lower bound is 6. In this also we can take that pair of elements least upper bound for 6 and 12 is 12, greatest lower bound for 6 and 12 is also 6. Okay, here whatever the pair of elements we are consider, for that pair of elements whatever the least upper bound and whatever the greatest lower bound exists in M1, the same LUB and GLB is also exist in the main Hussey diagram. Okay, hence we can say that M1 comma division relation is a sublattice of S24 comma division relation. Okay, so hence we can say that M1 comma division relation is a sublattice of S24 comma division relation. Okay, so this is a sublattice of S24 comma division relation. Okay, now consider M2 set. M2 is equal to set of 1, 2, 6, 12, 24. Okay, so here 1, 1, 2, 2, 6, 6, 12, 12, 24, 24. I am considering these elements from the main Hussey diagram. So whatever the Hussey diagram we are getting for elements of M2, so that this Hussey diagram can be taken from the main Hussey diagram. Okay, now we have to verify that the division relation between any pair of elements. So 1 divides 2. Yes. So that we have to draw the edge between them. 2 divides 6. So that we have to draw the edge between them. So 1 also divides 6 according to the transitive property. 1 divides 2, 2 divides 6. So therefore 1 also divides 6. So that we do not draw the edge between 1 and 6. 6 divides 12. So that we have to draw the edge between them. 12 divides 24, so that we have to draw the edge between them. 6 also divides 24 according to the transitive property. Whenever 6 divides 12, 12 divides 24, then 6 also divides 24. So that division relation between the elements of M2. So then this is the Hussey diagram we are getting from the elements of M2. That Hussey diagram can be taken from the main Hussey diagram. Now we have to verify that whether M2 is a sublattice of S24 or not. Okay, we can take any pair of elements, both the least upper bound and the greatest lower bound exist or not. We have to verify them. We can take the pair of elements 1 and 2. Least upper bound is 2, greatest lower bound is 1. We can take the pair of elements 2 and 6. Least upper bound is 6, greatest lower bound is 2. We can take the pair of elements 1 and 6. Least upper bound is 6, greatest lower bound is 1. We can take the pair of elements 6 and 12. Least upper bound is 12 and greatest lower bound is 6. We can take the pair of elements 2 and 12. Least upper bound is 12, greatest lower bound is 2. We can take the pair of elements 12 and 24. The least upper bound is 24, greatest lower bound is 12. We can take the pair of elements 6 and 24. Least upper bound is 24, greatest lower bound is 6. We can take the pair of elements 2 and 24. Least upper bound is 24, greatest lower bound is 2. We can take the pair of elements 1 and 24. Least upper bound is 24, greatest lower bound is 1. Okay, we can take any pair of elements of M2. Okay, so both the least upper bound and greatest lower bound exist. So that M2 comma division relation is a lattice. Okay, because we can take any pair of elements of M2. So both the least upper bound and greatest lower bound exist. So that M2 comma division relation is a lattice. Now M2 comma division relation is a sublattice of S comma 24 comma division relation. Okay, whatever the elements in M2, the same elements can be considered in the main Hussey diagram whatever the least upper bound and greatest lower bound exist for every pair of elements, the same least upper bound and greatest lower bound also exist in the main Hussey diagram. Okay, we can 1, 2, 6, 12, 24. Okay, 1 comma 24. Okay, LUB is 24, GLB is 1. 6 comma 12. LUB is 12, GLB is 6. 2 and 6. LUB is 6, GLB is 2. 1 and 2. LUB is 2, GLB is 1. Okay, we can consider these elements from the main Hussey diagram. Whatever the LUB and GLB are there in this one, the same LUB and GLB is also there in the main Hussey diagram. We can take any pair of elements of M2. Okay, hence we can say that M2 comma division relation is a sublattice of S24 comma division relation lattice. Okay, now consider M3. M3 is equal to set of 1, 2, 4, 8, 24. Okay, 1, 2, 4, 8, 24. Okay, so here I am taking 1, 1, 2, 2, 4, 4, 8, 8, 24, 24. Okay, so 1 divides 2, so that we have to draw the edge between them. 2 divides 4, so that we have to draw the edge between them. 4 divides 8, so that we have to draw the edge between them. 8 divides 24, so that we have to draw the edge between them. 4 also divides 24 according to the transitive property. If 4 divides 8 and 8 divides 24, 4 also divides 24. Okay. 2 divides 4, 4 divides 8. According to the transitive property, 2 also divides 8. 1 divides 2, 2 divides 4. According to the transitive property, 1 also divides 4. Okay, so that division relation is satisfied on every pair of elements. Okay, now we can take any pair of elements of M3. Both the least upper bound and greatest lower bound exist or not. We can take the pair of elements 1 and 2. Okay, least upper bound is 2, greatest lower bound is 1. We can take the pair of elements 2 and 4. Least upper bound is 4, greatest lower bound is 2. We can take the pair of elements 4 and 8. Least upper bound is 8, greatest lower bound is 4. We can take the pair of elements 8 and 24. The least upper bound is 24, greatest lower bound is 8. We can take the pair of elements 4 and 24. Least upper bound is 24, greatest lower bound is 4. Okay, we can take the pair of elements 2 and 24. Least upper bound is 24, greatest lower bound is 2. We can take the pair of elements 1 and 24. Least upper bound is 24, greatest lower bound is 1. Okay, we can take any pair of elements of M3. Both the least upper bound and greatest lower bound exist. Hence, we can say that M3 comma division relation is a lattice, because for every pair of elements, both the least upper bound and greatest lower bound exist. Hence, we can say that M3 comma division relation is a lattice. Now, we have to verify that M3 comma division relation is a sublattice of S24 comma division relation. Okay, whatever the elements are there in the M3, only that elements are considered in the main Hussey diagram. 1, 2, 4, 8, 24. Okay, we can take any pair of elements only 1, 2, 4, 8, 24 among them. Okay, for that pair of elements, what is the LUB and what is the GLB exist? the same LUB and same GLB exist for that pair of elements in this Hussey diagram also. So now here we are consider 8 and 24. Least upper bound for 8 and 24 is 24. Greatest lower bound for 8 and 24 is 8. We can consider 4 and 8. Least upper bound for 4 and 8 is 8. Greatest lower bound for 4 and 8 is 4. We can consider 2 and 4 for the pair of elements 2 and 4. LUB is 4, GLB is 2. Next we can take 1 and 2. LUB is 2 and GLB is 1. We can take 1 and 4. LUB is 4, GLB is 1. We can take 2 and 8. LUB is 8, GLB is 2. We can take 4 and 24. LUB is 24, GLB is 4. Okay. We can take 2 and 24. LUB is 24, GLB is 2. We can take 1 and 24. LUB is 24, GLB is 1. Okay. Whatever the pair of elements we are considered in both this Hussey diagram and this Hussey diagram. Okay. Same LUB and same GLB exist here and also here. Hence we can say that M3 comma division relation is a sublattice of S24 comma division relation. Okay. Now, so M1 comma division relation is a sublattice of S24 comma division relation. M2 comma division relation is a sublattice of S24 comma division relation. M3 comma division relation is a sublattice of S24 comma division relation. So both M1, M2, M3 are sublattices of S24 comma division relation. Okay, so this is the example problem on sublattices. Okay, thank you. Thank you for watching this video. If you like this video, please share this video to your friends and classmates. If you like this video, please subscribe my channel name. So, DIVVELA Srinivasa.